All right, good afternoon, everyone. Welcome to the final session on Two Port Networks. I trust you have all been keeping yourself safe from the Saharan dust and, well, as the interesting year of 2020 continues on its merry way. All right, just a couple of things before we get started. For this tutorial, there are a number of questions that I had asked you to complete for the past couple of weeks. I hope you have attempted them. I hope you have made the effort to check your solutions. I note on Schoology that there have been no input in the discussion forum. And so the only assumption I will make there is that the topic has been presented with some clarity and that you have completed the questions without any issue. That said, I'm going to take the time today and look back, well, not look back, but complete a question quite similar to what I had given you in your for one of your assignments or your homework. And hopefully you'll be able to, if you had challenges with the one that I gave you, based on what I will go through today, that will assist. Additionally, how we'll proceed for this tutorial, it will not be me coming here and just completing a bunch of questions. I'm expecting that persons will do some of the questions, and I will call on individuals for answers. I have taken note that only a few persons within the group have I'm getting feedback from, and it is important that everybody who is doing this module is up to speed on the material. So we're going to get started, and you can take this question. The resistors, in terms of how they are set out, is quite similar to the one that I gave you in class, or I gave you earlier, but the values have been switched around. So your focus this afternoon really should be on the approach to the question. All right? So take this question from me and let us get started. All right. So for this network, the question here asks us to determine from first principles the impedance and admittance parameters. Yes. So based on the fact, one, that we are told that we need to use first principles, it means that we need to start with a definition, right? Or, well, definition or a basic equation. So by definition, for the impedance parameters, Z11 is equal to V1 over Z1 with I2 being equal to 0, or in other words, with port 2 being open circuited. And based on the network that we have, yes, if we're looking at Z11 being V1, being V1 over I1, then obviously we're just looking at the impedance into port 1. And so for that, we have our resistance equation. So that's 4 in series with 2, which is in parallel with 3 and 2. Now note, of course, that the second 4 ohm resistor would not come into play because we have an open circuit. Yes, so we have the 3 in series with the 2. And if we simplify that, we have Z11 And that gives us 38/7. So Z11, impedance C looking into port 1 will be 38/7. All right? Everybody comfortable with that?
Yes, sir.
Yes, sir.
All right, cool. All right, now with port 2 still open circuited, we can also find Z21, right? So Z21, V2 over Z1, all right, with I2 being equal to 0. Z21 So in this instance, what we'll be looking at is how I1 will flow and where we would measure Z2. So, I mean V2. So V2 would be voltage, obviously, across the 2 ohm resistor, since I2 would be equal to 0. There's no I2 there. So the current I1 would be dividing between these two resistances. All right. And so we have the current Ix, and I'm just putting in Ix here for, my own purpose. So Ix would be 2I1/7. And so V2, which will be the voltage across that resistor, yes, V2 will be 2 times Ix, which will be 4I1/7. I then rearrange this expression. So I have that ratio. And in order to get that ratio, we will have V2 over I1 to be equal to 4/7. Now we look back at the network. Although we did not speak much to symmetry, but it is obvious based on this network that if I should look at the network from this port, yes, I would have 4, then 2, then 3, 2, 4. And if I go from this end, I'll get the same thing. All right. So whilst I showed you what a symmetrical network would look like, a symmetrical T and a symmetrical pi, this network as shown, whether I go this direction or this direction, the impedance would be the same looking from either end. All right. So it means therefore that this network is symmetrical. If it is symmetrical, then Z11 would be equal to Z22, and also Z21 would be equal to Z12. And so having found Z11 as 38/7, and of course Z21 as 4/7, yes, then it means therefore that Z12 will be equal to Z21, and Z11 is equal to Z22. So this would be my impedance matrix.
Dr. Isaacs, just a question.
Sure.
When we're working out Z21, right, sir, we're doing current divider and then we multiply it by the resistance to get the voltage across it, right, sir?
That's what we did for this in this instance.
Okay, sir. So why is it that we neglect the fact that the circuit is a parallel circuit in terms of the resistance for the denominator?
All right, let's make sure we understand the question. All right. What we're finding is a relationship between I1 and V2. Agreed?
Yes, sir.
Okay. Now, based on where V2 is, if I2 is equal to 0, meaning we have an open circuit, would you agree that the voltage across this resistor would be 0?
Yes, sir.
Okay, which means that the voltage here would be V2. Do you agree with that?
Yes, sir. Yes, sir. I agree.
Okay. Now, I1, would all of I1 pass through the 4 ohm resistor?
Yes, sir.
And when it gets to this point, what happens to it?
It splits
Between?
between the 2 ohm and the 5 ohm resistor.
All right. So what's the question now? What did you say we're ignoring?
Yes, sir. All right. You see how they're parallel, the 2 and the 5? When we're summing it, we don't sum it as parallel. I was wondering why we sum it as series.
You mean this resistor and this resistor?
And the other 2 ohm resistor on the other side.
This, the current that comes here, you just said it divides here between these two, between those two branches. Yes?
Yes, sir.
If the current is dividing, then how are they connected?
They're connected in parallel, sir.
Yeah, so I'm doing current division between this and these.
Yes, sir, but usually in current division, wouldn't we sum
No,
it
no,
as
I
two
don't
parallel?
I don't want to talk about no usually. Look at the circuit and deal with the circuit that is before you. What you have, these, do you agree that the current that passes through this 3 ohm will pass through the 2 ohm?
Yes, sir, full agreement.
So if the same current passes, if the current leaving the 3 is the current entering the 2, what does that say about the 2 resistors?
That they are in series.
Okay, so what's the issue?
Sir, the denominator. Why is it 7 and not 2 parallel 5?
It can't be 2. We're using current division. So you're dividing between 2 and 5. So it is 2I1 over 2 plus 5. That's the current divider rule.
Okay, sir.
If you go back to the original circuit, it tells you, there it is. You see, that's one of the one of the reasons I have been stressing the use of the resistance equation. Now, I know I did say that persons are free to use whatever method they learned in high school, but there's a reason I went this route. Because at this level, we don't have time to be stressing over those minor things. This equation tells you everything. It tells you that 2 is in parallel with 5. Here it is. All right, so you know that the current that passes through the 4 goes directly to the 2 and the 5, which are in parallel. So the current division is between these two. IX would pass through the 5 ohm. Yes, IX would be the current through the 5 ohm. So it will be 2 times I1 over 2 plus 5. That's IX. All right? Okay. So back to where we were, which is that the impedance 1/7 . 1/7 to 38, 4, and 38. Okay, so that's the impedance parameters. Now, for the admittance parameters, we're looking at the short circuit parameters. So it means, therefore, that we will be short circuiting port 2. So there's a short circuit for port 2. Now, that changes the entire circuit. Right? That changes the entire circuit. So now, with that port short circuited, the total impedance, or going back to our equation, all right, note the change here. The 3 is now in series with the 2 and the 4, which are now in parallel, because I have now put in the short circuit. All right, and we are looking for the admittance parameter. So in finding the admittance, again, we want the relationship between I1 and V1. Now, if we can find the total impedance, yes, then we know that Y11 would be equal to 1 over ZT. So what we're going to be doing here, now that we have that short circuit in place, what we'll be doing, we find the total impedance, that's our equation, and all right, so that's my equation. And again, in going through this, I'm once again going to highlight the benefit that comes from having, or from being able to write the resistance equation or the impedance equation. All right. So from here, we simplify the 4 and the 2 in parallel. Yes, we get 8/6 or 4/3. I add 3 to that. All right, I add 3 to that. I get 13/3. I make that in parallel with 2. So I have 2 times 13/3 over 2 plus 13/3. Yes. And we get 26/19. And then I add 4 to that, and we get 102/19. All right. So 1/ZT, which is, of course, as we said earlier, would be Y11, is now 19/102. Okay. With the short circuit still in place, everyone have this? Is there anybody who's still writing?
Yes, sir.
Somebody still writing? Okay.
No, sir.
Go again.
I said no, sir.
Oh, okay. With the short circuit still in place, what I've introduced are Vx and Vy. In other words, I just want the voltage at these 2 points. So this is Vx and this is Vy. All right. The reason I'm doing that is because I want to determine the current passing through the 4 ohm resistor. All right. So whilst I use current division for the impedance parameters, I'm gonna now use the voltage divider rule for in finding the admittance parameters. Now, I want to just show you quickly. In finding Vx, it's of course the voltage not across the 2 ohm resistance, but across everything beyond that point. Fair enough? The quickest place to find that information is back here. Because I know I'm dividing between 4 and the rest of the circuit, which is 26 over 19. So I just quickly go back to my resistance equation and I have what I'm dividing between. Yes? So in doing that, Vx, the 26 over 19 times V1 over 4 plus 26 over 19. And I get 26 V1 over 102. So that is our Vx. All right. We can also find everybody comfortable with this? All right. Now, Vx, yes, it's across there, but it is also the voltage across that section of the circuit. So I can now, I'm going to say ignore, but it's the same voltage beyond the 2. It's a voltage in front of the 2, it's a voltage beyond the 2. All right. So again, I go back to my resistance equation. And what are we dividing between? We are dividing between 3 and the rest of the circuit, which is 4 over 3. All right. So I have my Vx. So I now want to find Vy. Vy is the voltage beyond this point. So Vy is equal to 4 over 3 times Vx, that's Vx, 26 V1 over 102, over 3 plus the 4 over 3. And that gives us 8 V1 over 102. So that's the voltage across the 4 ohm resistor, because the 4 ohm resistor is in parallel with the 2 ohm. Right? And we had already established that from our equation. So I can now find the current through the 4 ohm resistor because I know Vy. So the current through the 4 ohm resistor would be Vy over 4 I'm I'm sorry, this hold this part. Vy over 4 really gives you minus I2. All right? So Vy over 4 is equal to minus I2. All right? Which means, therefore, that 8 V1 over 108, 102, yes, times 1 over 4, that's equal to minus I2, which implies, therefore, that I2 over V1 is equal to Y21, which is minus 2 over 102. Any questions on what I have just done for the admittance parameters? Does anyone have any questions on this? All right.
Sir,
Uh-huh.
even in a test situation where we already know that the impedance, the entire matrix for the impedance, the inverse of that would give us the admittance. Could we just do that, or do we have to? For a question like this, do we have to go over
What did the
all these
question
steps?
ask you for?
It asks using the first principles to determine the impedance and admittance parameters.
All right. So if you invert the matrix, is that first principles?
No, sir.
Okay. All right. So you have your answer then. We have already established that the circuit was symmetrical. So it means, therefore, that Y11 would be equal to Y22 and Y12 would be equal to Y21. You see, first principle, deriving the values, first principle. All right. So you now have this as your matrix, your admittance matrix. All right. So what I want you to do now, what I want everybody to do, based on it, well, I think the second part of the question, I didn't put it in. But anyway, just take this part be the question because that is what I had given you in the assignment or the homework. I won't call it assignment. The homework. I had asked you to verify that the parameters, the value of the parameters by using the conversion matrix. So the question that was just asked about whether or not you could just invert. Yes? No, you get a chance to do it because that's what the second part of the question would have asked. All right. So what I want you to do is to calculate or verify that this is true or the values that you have calculated are accurate by inverting invert one of the matrix, whichever one you choose. So you can invert Z to Y or Y to Z. All right, and verify that the values you calculated are accurate. So I give you so 5:30. I give you 5 minutes for that. You don't need more than 5 minutes.
Sir, we got it verified, sir.
All right. Have we been able to verify the values?
Yes, sir.
Yes, sir.
Yes, sir.
All right. Miss Chan, you got the values?
Yes, sir.
Excellent. Miss Barrett, how are you? You got the values? Were you able to verify?
Yes, sir.
Okay. Whoever is MM, I'll be removing you from the group in a few minutes, unless the name comes up. There's a bit of information there.
Sir, that's me. I forgot to change it this time. Sorry about that.
You better come out and come back in. Anyway, all right. So, folks, let's go back to the network. Who is that? Campbell, Conrad, that was you?
Yes, sir, that's me. I'm changing it now.
Good, man, good. Okay, so where is our circuit? So this is my network. But this is really where I wanted to get to today. What if I divided this network in two? What if I split it down the middle? Right? Could easily just a minute. Yes. What if I split the network in two? So I have the 4, 2, and instead of the 3 ohms here, I have 1.5. Right? What I would then end up with, this would be half of the network, yes? And you agree that the other half would then look something like this. Right? So that would be 1.5. This would be 2. And this would be 4. And if I push them back together, I'll get back the original network. Agreed? So what we're going to do is to, and you know, this would be the output of network 1, and this would be the input of network 2. And over here would be the output of the combined networks. Now, because I have the output of one network feeding into the input of another network, then obviously it means that they are connected in cascade. Would you agree with that? So we can call this A, and we can call this B. So network A would be connected in cascade with network B. So I'm going to start by analyzing network A. And because they're in cascade, we know that the overall transmission parameters will be equal to the product. The overall transmission parameters would be equal to the product of the transmission parameters of A times that of B. All right? So that's our objective. So I'm just going to go directly to finding the transmission parameters. You, of course, if you feel more comfortable, this what we're looking at here is a simple T network. If at this stage you're more comfortable finding the admittance first, then fine, go ahead, do that. If you're more comfortable with finding the impedance, do that, and then convert them to transmission. That's the freedom that you have. But for this afternoon, we're going to just find the transmission from using first principles from scratch, right? So A, we know is equal to V1 over V2 with I2 being equal to 0. If I2 is 0, it means that we have an open circuit at port 2. Yes? And so A in finding A, what we're doing is finding a relationship between V1 and V2. V1 and V2, with this open, it means that V2 would be the voltage across the 2 ohm. Right? That's V2. And if that is V2, then V2, we're just applying voltage divider. Right? Because the 4 and the 2 are in series. So V2 is equal to 2V1 over 6. Yes? What we are interested in finding is 1 over 2. So 1 over 2 would be equal to 6 over 2, which is equal to 3. So A is equal to 3. Everybody comfortable with that?
Yes, sir.
Yes, sir.
All right. Now, with the output port open, I'm also going to find C. All right. So in finding C, C is equal to I1 over V2 with I2 being equal to 0. Okay. So C is equal to I1 over V2 with I2 equals 0. Same port conditions for A and C. If we go back to the network, remember what we're looking for is a relationship between I1 and V2. I1 would flow through the 4 and the 2 ohm resistor. So the voltage across the 2 ohm resistor would be 2I1, which is what we have here. All right? And that voltage is V2. So it means that C is equal to a half. All right? Any questions?
Sir, can you repeat?
Go one more time, sir.
Yes, sir. Repeat it one more
Wait,
time.
that one, sir.
We're finding A. These are our transmission equations. Fair enough?
Yes, sir.
All right. Those are our transmission equations. With I2 being equal to 0 A is equal to V1 over V2. What we mean by I2 equals 0 means that port 2 is open. So if port 2 is open, it means that V2 would be the voltage seen across the 2 ohm resistor. With respect to V1, the voltage across the 2 ohm resistor is 2V1 over 6. And we know that that is equal to V2. So therefore, V1, let me do everything. Just a minute. It means that 2V1 equals 6V2. V1 is therefore equal to 3V2. So V1 over V2 equals 3. For C, look at the circuit. Remove all of this thing. For C, where look, if I2 is 0, then it is I1 over V2. Question, what is the relationship between V2 and I1? I1 is the current that will flow through the 2 ohm resistor, so the voltage across the 2 ohm resistor we already know is V2. So V2 is equal to 2I1. So I1 over V2 is equal to a half. Okay. So we have A and we have C. I now go to B. By definition, B is equal to V1 over minus I2. Again, let's go back to the equations. I'm trying to find B. So it means that V2 is made 0. So I'm left with V1 equal minus B I2. So B is equal to V1 over minus I2. All right? So that's the definition we have here. So if V2 is now equal to 0, if V2 is equal to 0, what I have done is that I have now short circuited port 2. So if I put the short circuit on port 2, yes, if I short circuit port 2, it means that these two are now in parallel. Yes. So we have here and there should be two let's see. All right. This should be two. All right, scratch this. If we go back to the circuit, it will be 2 in parallel with 1.5. Everybody agree with that? Remember what we are getting at is B. Okay, so it's 2 in parallel with 1.5, which is equal to 3 product over sum over 3.5. Right? So those two resistances, let's scratch this out. It will be 2 in parallel with 1.5, which gives me 3 over 3.5, which is equal to 6 over 7. All right? So that's the correction for that. So the voltage across the 2 ohm, right, will be the voltage across that parallel branch. I'll go back to the circuit. So what we are interested in is the voltage across this. Right? So it's an entire parallel branch. With this short circuit in place, we are looking at the voltage across that parallel section. So what we have is the voltage being divided between 4, yes, and 6 over 7. All right. So it is 6 over 7, which is that parallel section, times V1 over 4 plus 6 over 7. And that is equal to 6 over 34. That's 28 plus 8. That's 34 over 7. All right. The 7's cancel, so we get 6 V1 over 34. Okay. So that's V2 ohm. And what we're interested in B is V1 over I2. So I have the voltage across the 2 ohm, but it's also the voltage across the 1.5, which would give me I2. Yes? So if I do that, right, so I2 minus I2 would be equal to the voltage across the parallel section divided by the resistance, or times 1 over 1.5. And this gives us 4 over 34. So minus I2 is equal to 4 V1 over 34. But what are we interested in? We're interested in V1 over minus I2. So if we cross multiply here, we get 34 over 4, which is equal to 17 over 2. All right. So that's B.
So, sir, we're negative sign gone.
Pardon?
So, where's a negative sign?
It's right here. In what direction would the current be flowing given that voltage?
So, it'll be flowing from left to right,
Okay, in what direction is I2 flowing?
right to left.
Question answered then, eh?
Not really, sir. It's just we calculate I2, so I haven't seen you use any negative sign in the
I'm
equation.
saying I2 would have been going in what direction?
Right to left.
Okay, the voltage you just calculated, in what direction would it cause a current to flow through the 1.5?
Left to right.
So what have you calculated? Is it the negative
Negative
of
of
I2?
I2 there. Yes, sir.
So you're all right, man.
Thank you, sir.
Okay, now for D, these are also calculated with V2 being equal to 0. In other words, with the short circuit at port 2. And what we're looking at is the relationship between I1 and I2. So we go back to the circuit. All right. Oops. All right, so there's our circuit. And we are looking at what connects I1 what connects I1 and minus I2. Obviously, minus I2 will be going in that direction. All right? So if I1 is the current coming to this point, all of it would pass through the 4 ohm. Some will go through the 2, and some will go through the 1.5. All right? So the current through the 1.5, can now go back to what we're looking at. The current through the 1.5 is therefore 2I1 over 2 plus 1.5, which is 3.5. All right? But what we are interested in is this ratio. So in getting that ratio, yes, it should be up here. All right, so I1 over minus I2 is equal to 3.5 over 2, or 7 over 4. And so our final matrix all right, will be 3, which is A, B 17 over 2, C a half, and D 7 over 4. So students, listen, the bottom line is you simply need to know the initial equations, be able to write the definitions in terms of the voltage and current relationships, and apply basic circuit analysis. All right. And I suppose the difficulty is that sometimes you're writing a lot without being able to use a calculator. Right? But there's no easy way around this. All right? So now that we have gone through finding the transmission parameters for half the network. Now I've answered some questions that are not specifically related to two-port networks, or really related to Ohm's law. But do you have any challenges or questions regarding what I have just done in terms of finding the transmission parameters for half of the network? Does anyone have any questions with respect to what we just did from a two-port network standpoint?
Sir, I had an issue. I couldn't figure out how you did B, sir. I didn't really understand how you got B.
D?
B, sir,
Alright.
boy.
Oh, B.
Yes, sir.
All right. So let's go from first principles. You're comfortable with this? With the
Yes, sir.
definition?
Yes, sir.
All right. So let me get some space. All right. So this is the network. This is the network. All right. Give me the definition for B.
V1 over minus I2, sir. When the output is short circuited.
No, man, that's not what we said. When V2 equals 0.
Yes, sir.
All right. No. Well, you said it just now, but I still can ask for you to repeat it. V2 being equal to 0, what does that mean?
The output is short circuited, sir.
So I'm going to put in my short circuit. So there is a short circuit. All right. This was 4 to 1.5. All right. I2 is the current going in that direction. So if that is I2, in what direction is minus I2?
From left to right.
All right. So that means that I2 is going there. Minus I2 is going there, right? So what are you interested in finding? Minus I2, where is it flowing?
Through the 1.5.
Through the 1.5. Beautiful. No problem. Beautiful. Next question. What information do you need for about the 1.5 for you to be able to calculate the current I2? What are information you need?
The voltage.
So you need the voltage across the 1.5.
Yes, sir.
All right. Now that voltage, remember now, the definition talks about V1. What is the relationship between V1? Yes? That's a relationship between V1 and the voltage across the 1.5.
The V1 is split between the 4 ohm and the 1.5 and 2 ohm in parallel.
All right. So before I don't want to write all of that detail. All we're gonna say is that V1, and let's call this, I'm gonna call this Vx, all right? So Vx is equal to, let's call that Z rest of circuit, times V1 over Z rest plus 4. You agree with that?
Yes, sir.
All right. So based on that expression, the question is, what is Z rest? What is the impedance for the rest of the circuit?
The 1.5 and 2 ohm in parallel.
Is this the same person that we're talking? I wasn't looking who was speaking to me before.
Yes, sir. Crossdale.
Yes, the same person. Okay. All right. So, so we have the 1.5 and the 2. Yes, they're in parallel. And what is the combined impedance resistance? Hello?
Yes, sir.
What's the combined resistance of the 1.5 and the 2? How are you going to find? They are in parallel. Come on, quick. This is better.
It will be 3 over 3.5.
All right. The product over sum, 3 over 3.5.
Yes, sir.
So 3 over 3.5 times V1, yes? And then 4 plus 3 over 3.5. All right? Based on our calculations, yeah, that gives us 6 V1 over 34. So now you have the voltage across the 1.5. Remember what the objective was? You want the current through the 1.5. But you need the voltage. This is the voltage. But it is in terms of V1. So I2 minus I2 is equal to Vx, which is equal to this, over 1.5. That is 4 V1, 134. All right.
See you, sir. All right, thank you, sir.
Yeah, man, no problem. All right, so question by Mr. Crasdale, I hope will make it, would have provided some clarity for other people who were afraid to ask.
Most
So you
definitely.
have the T matrix for that network. Anybody else have any questions regarding what we just did? Going once, going twice. All right, sold. There be no further question from you. I have one for you. I want you to look at the other half of the network. So what I want you to do now, use whatever method you choose. Whether you want to find the admittance and convert it to T, be my guest. But I want you to find the transmission parameters for this network. Quickly, you only have, I'm giving you, all right. I'll give you 8 minutes on this one. All right, so I come back to you at 6:15. we want to start the ball rolling.
Sir, I get for A 3.5 over 2. C, I get a half. For B, I get 18 over 4. And D, I get 3.
D, you
I
get
got
3.
some.
D, you got 3. A, you got what?
Yes. 3.5 over 2.
Okay. Mm-hmm.
For C, I got a half. And then for B, I got 18 over 4. Or 9 over 2.
Okay. Anybody else got anything different?
Yes, sir. For B, I got 17 over 2.
For B, you got 17 over 2.
Yes, sir.
Yeah.
Sir, for B, I got 7 over 2.
I got something else.
All right.
Sir, I got 3.46 for A, 17.29 for B.
Oh, hold on. Let's keep in the tradition of fraction. So, A,
Sir, I
go ahead.
don't have it in fractions. Sir.
Oh, so you depend on the calculator.
Sir,
Did you derive the parameters from first principle or you converted?
I did mine from first principle, sir.
Yeah. So you got similar to what Adams and Miss Great okay?
I think,
You
let
think?
me just tell you, I had 3.5 over 2 for A.
Mhm.
For B, I have 17 over 2. And for C, a half. And D, 3.
Okay. Okay. All right. So you would have noticed, right? This one I didn't put in because it was important for you to do it. Right? So 7 over 4, which is the same as 3.5 over 2. 17 over 2, 3 and a half. All right, that's what you got for TB.
Yes, sir.
All right, excellent. All right, so what I wanted to, well, you would also note that this was kind of similar to TA, right? I don't know how many. That we had 3, and this was 7 over 4 down here. And then C, and then this is 17 over 2. All right. So all they have done is to look at the network from the other end. Anyway, I don't want to give you anything for you to try and remember. I want you to get into the habit of doing it from scratch, all right? So what I want you to do for me now, because the two networks, remember we said that we had just split them in two. If we put them back together, they are in cascade. So I want you to find T, which is equal to TA times TB. So let's work that out for me quickly. So we're working out the overall transmission parameter. So you just multiply those two matrices for me. And it must be A times B, not B times A. All right, because it most follows how the networks are connected. And this one you're going to just stick in the calculator, right? Anybody?
Sir, I got 9.5, 51, 1.75, and 9.5.
So this is the transmission parameters for the entire network. All right? Anybody got anything different?
Yes, sir.
Yes, sir.
All right,
So,
all right. Before you go any further, if you get anything different, you are incorrect. All right, this is correct. Remember, it is A times B, not the other way around. Because remember, you're going to be putting network A here. All right? And you're connecting it in cascade to B. So Forrester, what you got? So Forrester?
Sir,
What result you got?
I've been driving, sir. I just stepped out of the vehicle a while ago. So I've just been following, but I haven't been able to actually look at it.
All right.
Sir.
Yes, Mr. Busa.
I got 9.5. I didn't get the 51. I got 29.75. I don't know.
Did you do the product by longhand or you use a calculator?
Calculator I used.
Oh man, so wrong there.
Okay.
Sir, that's the same thing I'm getting, sir.
Same thing I'm getting.
Same thing.
All right. Well, here is where we are now going to test to see whether or not we are correct. All right. So to ensure that what we have gotten is correct, what you are going to do is to convert this T matrix. We don't have to worry, because we have the answer already. You're going to convert the T matrix to Y. Convert that to Y for me. All right, so the matrix that you have gotten, convert it to Y. And I'm just double checking to make sure that what we have here is correct. So that's 3. All right, well, I just double checked it. It's 9.5, 51, 1.75, and 9.5. So you're going to convert that to Y. The matrix you're using to do that you're using to do that. And all right, we have what's on screen? Everybody?
Yes, sir.
All right, so the matrix you're using to convert to Y is D over B minus delta T over B minus 1 over B and A over B. All right? And this, if we keep it in the fractions, it makes life a lot easier. B is 51. All right, so we have here 9.5 over 51. Yes? Then the delta is minus 1, is 1 rather. So we have 1.
One over 51.
Yeah, I don't know. It wasn't marking. I don't know what was happening. 1 over 51. All right, and then down the bottom we have minus 1 over 51. And then we have 9.5 over 51. All right, now if I multiply what's in the matrix there by 1, but I'm going to write 1 as 2 over 2. All right, so I multiply everything in the matrix by 2 over 2, which is 1, right? Then what we end up with is 19 over 102 minus 2 over 102 minus 2 over 102 and 19 over 102. Look familiar?
Yes, sir.
Yes, sir.
So that is the admittance matrix that we had before. Okay, folks?
Yes, sir.
Yes, sir.
So what are we saying here? You have networks that, may look a little complex. You can break it down. You can break it down into 1 or 2 networks. You can connect them in cascade, in series, in parallel, in order to get the overall or the parameters for the combined network. All right? So you have that flexibility. So what I'm going to do is to go back to a question that we did some time ago. Did it, I think, last week. Yeah, it was last week. So let's go to that question. Okay. So remember this network. Yeah? Now, we have here, I'm gonna just go where we are. Good. So what I have here, we have the network, we have the hybrid parameters. So these are the hybrid parameters. All right? Now, based on what we have done so far, we can convert this to the transmission parameters. Fair enough? And if we all right, so we can convert that to transmission parameters. These 3 resistors, we can consider them to be a network. So instead of what we did, where we found this relationship, which for some persons may be a challenge, what you could have done, is to treat this as a 2-port network which is then connected in cascade with our original network. Everybody with me?
Yes, sir.
So for those three resistances, what I'm going to give you the transmission parameters. All right, so the transmission parameters for those three, 4 over 3, 110 over 6, 1 over 15, and 5 over 3. All right? So those are the transmission parameters for these three resistors. You can convert the H parameters to your T parameters. So you then have TA, which is what you have up here. Yes. And then you would have TB, which is for this. And so T would be equal to TA times TB. Everybody clear with that? Now, how are you going to check to see whether or not doing this is correct? Remember now, the combined network of TA and TB, of networks A and B, this will now be your I1. The I1 will be the current flowing here, yes? Which means that this would be equal to V1. Is everybody following me?
Yes, sir.
Question, sir. Where is network A and network B?
They're marked. So A right here. A is that, and that's B.
Oh, okay.
All right. So we find T, which is TATB. Now, as I was about to say, to validate or to verify whether or not what you have done is correct. I'm not going to do this for you, because I'm getting the impression that not much work is being done on your side. But you're going to have to prove me wrong. I had given you, I had done the substitutions. So I had given you these as the substitutions, okay? And said that you should complete it. So once you have found T, which is equal to A times B. All right? Once you have done that, you would then have your equations, which says V1, I1 equal AV2 minus BI2 and CV2 minus DI2. All right? From the network, V1 is 75. And of course, you know that V2 would still be minus 3 I2. So you can make the substitution for V2 in both equations. And in doing that, you should, if what you have done is correct, you should get the same value for V2 and I2 using this method as using the transmission parameters. All right, so I have already given you the transmission parameters for network A. You have the hybrid parameters for network B. As I said, you do the conversion and everything should work out quite fine. All right. All right, now we're almost out of time. So what I'm going to do is to go quickly to, I'm going to do the first part of the question I gave you I left you with last week. Any questions to what I just said? All right. So let's go quickly to the question that I left you with last time. All right. So here we have a rather simple looking question. All right. And the objective was for you to find the hybrid parameters. You have to find the hybrid, the admittance, and the impedance parameters. All right. Let's see who we still have there. So Kamika. Kamika? Oh, you're only hearing name? Okay then.
Oh.
So Johnson.
I'm here, sir. Which one is Johnson?
Kenyatta.
Oh.
Yes, sir.
All right. Now, given all that we have said so far, I don't want answers. I just want to have a clear understanding of your approach to doing this particular question. What would be your approach, given what we have done today?
Sir, based on what I can see, the network is a symmetrical network, sir. So it's split it in where the 6 ohm resistor is, sir.
Why you say it's symmetrical? In what way is it symmetrical? What does symmetry mean?
Sorry, sir. I just saw my error. I thought it was 7. I thought it was symmetrical about the 7-5 and then 7-5 again. So I thought it was 7-5.
Okay, all right. No problem. Good that you pick it up. All right. Okay, so would it change how you approach it, the question?
Yes, sir. It would, sir.
Would it? Well, so Mr. Farhan, you agree with him? You think he was on the right track?
Sir, it would, sir, if you look into the network from the left side, sir, that is where
Hold on,
the
it's
7.
Farhan, is Farhan talking to me? Or is Johnson?
Sir, repeat that.
Yeah, I was asking Mr. Farhan whether or not Mr. Johnson's decision to change his approach.
What was that, sir?
To the question. Oh, you weren't listening?
I didn't hear it.
Oh, I see. Okay. So Jeffrey?
Yes, sir.
What approach?
Was on the right.
He was on the right track.
Yeah. That's
You mean you would split it at the 6 also?
Yeah, 3-3. Working from there.
Oh, so you would split the 6?
Yeah.
Okay. That would work. That would work. Yeah, that would work. But it may not be as easy as. Anybody see anything easier?
Let's one side of the 6, sir.
What's that, Mr. Watson?
Sir, split it, sir. So one of the networks would have the 6 and one wouldn't. I'm not sure that would be easy.
So you would cut it like that?
Yes, sir, for instance.
All right. No, not a problem.
Sir, I have a question, sir. Would it be also, like, could you split it into 3 networks, sir, and work it as 2 pi networks and have the 6 in the middle, sir?
Who was that?
Johnson, sir, Kenyatta.
Oh, yeah, but you haven't given up. So you're saying make it 3 networks?
Yes, sir.
And if we now have 3 networks, you're saying that we have 3 networks in Cascade? Is that what you're saying?
Sir, wouldn't they be in...
Johnson. Oh,
yeah.
Continue that one. Would they be in what?
Wouldn't they be in Cascade, sir?
No, you're asking me?
I'm saying, sir, it would be one Pi network being cascaded with a 6 ohm resistor network, and then in Cascade with another Pi network, sir.
All right, no, and you're perfectly correct. Now, what is beautiful, Mr. Johnson, about the 2 Pi networks? Is there anything interesting about the 2 Pi networks?
Sir, the 2 Pi networks are symmetrical, sir. So the results
No, they are not symmetrical, sir. They are not symmetrical.
Sir, the 2 Pi networks are they are the same.
They are similar.
Yes, sir.
They are not symmetrical. Yes, they are similar.
Yes, sir. That's what I meant, sir.
No, sir, that's not what you meant.
All right, sir. I'll take the correction, sir. Similar, not symmetrical.
Thank you very much, sir. So they are similar. So what that means is that if you were to find the transmission parameters for this network, they'll be the exact replica for this. Yes? So it means that you only will be looking at the transmission parameters for 2 networks, which would be this Pi network yes, and of course this network. All right, and we can put in the I1s to just make sure. Yeah. And then we have I1 there, or I2 here. We have our V2, or V1, or I1, I2, I1. Is this thing messing with me? All right, so let's give me my I2. All right. So that's how we break down the network. Okay, gentle people?
Yes, sir.
All right.
But sir, it will still be important to do the multiplication as they would appear in the network, right, sir?
You can never change that. It must be in the same order of how they are connected.
Yes, sir. Because I was almost tempted to say TA squared times TB.
Yeah, don't yield to temptations. Don't yield to temptation.
Just making sure.
All right. Now, I'm going to give you the transmission parameters for the well, I'll just give you it for the pipe, but you know what? Let me not give it to you. I want you to try and calculate the parameters for the Pi network and also the parameters for the 6 ohm. So, let's deal with the one with the 6 ohm. All right. All right. So we're wrapping up, but let's just deal with the 6 ohm. What time is it? It's now 13 minutes to be over. All right, folks. It's 13 minutes to 6. So what I'm gonna ask you to do, while I deal with the register, I want you to find the transmission parameters for that 6 ohm resistor. All right, quickly, just find that for me. Marcelo Clark. Is Mr. Kamika back? Mr. Kamika? Alright. Waste time. Who is Dre Morrison? You know what? That one, don't come back. All right. Okay. All right. Are we ready?
Yes, sir.
Yes, sir.
So what's the matrix?
1.
Oh, you said you did
1.
1,
0, 0, 1.
1,
6.
6.
1 over 6.
1 over 6.
1 over 6. 1.
What I'm asking for the transmission parameter.
Sir, it's 0, 1, 1, 2, 2, over 0. So that's 0, 1, 1, 0.
All right, quickly. Let's go through this. What is A?
1.
1.
No. How do we find A?
V1 over V2.
V1 over V2.
And I2 equals 0.
Based on this circuit, right? Are the two voltages equal?
Yes, sir.
Is V1 equal to V2?
Yes, sir.
Yes. So it means that this is correct. All right. For C, for C. C is equal to
1 over V2.
1 over
I1,
6.
I1 over V2. Okay? Now what is I1 equal to from this circuit?
Minus I2.
Huh?
Minus I2, sir.
Yeah, man, but what is I1 equal to from this circuit?
V1 over
V1 over 6.
This circuit that you are looking at, what is I1 equal to?
0.
Must be 0. There's no closed path, so there's no current.
Yes, sir. So you missed it.
So I1 is 0. So it's 0 over V2. That's 0. Now I close this. What is B given by? B is V1 over
minus I2.
Minus I2. All right? Yeah. What's the relationship between V1 and I2?
V1 and I2, 6.
What is the relationship between V1 and I2? Just give me just tell me what, right?
6.
So V1 is equal to what?
I2.
Huh?
6I2.
Minus 6I2. Because the current will be going in this direction, no?
Yes, sir.
All right. So V1 over minus I2 is 6. And that's B. All right? Everybody with it?
Yes, sir.
With the short circuit in place, what's the relationship between I1 and I2?
The same thing. That's the same thing.
So I1 is equal to minus I2. So D would be equal to 1 over 1. So D is equal to 1. So that's it. Ladies and gentlemen, first principles. Now you have me worried whether or not you have done justice to Networks 1. I will leave it at that. Just some quick notes. Well, as I had indicated last time, that this now marks the end of what will be on the first assessment. All right. As it relates to that first assessment, I have removed a few persons from the module based on non-attendance for a couple of weeks. Some of them I've communicated with, some have communicated with me. Now you need to go and complete your registration online because you will not be allowed to do the assessment unless you are fully registered for the module. All right? So we're not going to test out the module and then decide whether or not to pay for it. That's not how it's going to go. But I think personally that, you're in a good place to successfully complete the module. So, that being said, I see you, God's willing, on Monday at 5, where we will get started with transients. All right, so you'll have 2 classes in transients that will not upset, so to speak, your preparation for 2-port and network theorems for your test. You can submit queries in the discussion portal. All right, that's where I'm going to receive queries regarding what we have done or your preparation for the test. All right, I'm not going to receive it through the mail. I want it in the discussion forum so that everybody can benefit from whatever feedback is provided. All right. So that said, have a good evening. All the best and keep safe.